Hi everyone. So we are going to be talking today about multiplying and simplifying radical expressions. And we have a certain rule for this. We say that the nth root of a multiplied with the nth root of b is nothing else but the nth root of a times b. So in other words, you can just multiply the radicands and combine these radical signs. Now we have to be careful. We have seen already for an example earlier on that for addition, this does not work in the same way. This is not working for addition. Multiplication is special. So here's an example how this might come in handy. If I have the cubic root out of 2 multiplied with the cubic root out of 4, then I can multiply the radicands and I will get the cubic root out of 8. 2 times 4 is 8. Now 8 is nothing else but 2 cubed. And that means now that the cubic root out of something cubed is equal to 2. So the moral of the story here is this, that the cubic root out of 2 is not a nice number. The cubic root out of 4 is not a nice number, but if I multiply both of these, I will get something that is fairly nice, the number 2. Let's have a look at another example. The 7th root out of 2x multiplied by the 7th root out of 6x cubed. We do not put multiplication signs in between like this if we are actually multiplying two things, as you know, just like between the 2 and the x and the 6 and the x cubed. So what we have here, is the 7th root out of, 2x times 6x cubed. And now we are just simplifying the radicand. We are multiplying this out and we get, 2 times 6, that is 12, and x times x to the third is x to the fourth. And this is it. The 7th root. For future examples, we are going to use something like this going backwards, but we are going to see exactly when and how this is useful. So, right now, it will come in handy. We are using factoring to simplify radicals. That means, if you look here on the right side, if I have the square root, for instance, of a times b, then I could break this up into the square root of a times the square roots of b. So, if I have two factors underneath my radical sign, then I can split those ones up right in the middle. Now, the reason why we are going to do this, or when we are going to do this, is when I have turned this right here into a perfect square in this case. Because the square root out of something squared, we can figure out what that will be, and we might end up just with a little bit radical left. Let me demonstrate here with this example. We have here the square roots of 28. Now, what I'm trying to do is, I'm looking for two numbers whose product is 28, but one of the numbers has to be a perfect square. So 28, for instance, has a few factors. 2 times 14 are two factors of 28, but 2 and 14 neither are perfect squares. 28 is also 4 times 7. Now this will be the interesting factorization in this case. 4 times 7. Why is this the interesting one? Because if I break this up now, the square roots of 4 times the square roots of 7, then the square roots of 4 can be simplified. That is just going to be 2 times the square roots of 7. And I have still a little bit radical left, the square roots of 7, but I pulled underneath out as much as I could. This is the idea that we are going to be using for the next one as well. The difference here is that I'm not looking at perfect squares, I'm looking at perfect cubes. So I have to look at everything underneath my radical sign, and I'm planning on putting perfect cubes here times the rest that I will just collect. So I first look at the number 32. The number 32, one moment, 32, is there a perfect cube in there? Perfect cubes are 8 times, let's see, what do we have? 8 times 2 raised to the 5th, 8 times 4. So 32 is nothing else but 8 times 4, 8 being a perfect cube. Then I look at my variables. X squared is not a perfect cube. The exponent is not even big enough to have a 3 in there. But y cubed is also a perfect cube. So I split this radicand now into 2 factors, into 8y cubed times 4x squared. Nothing really changed. This is still 32x squared y cubed, but this one right here are perfect cubes, perfect, and this right here is just the rest. And what I will do now in my next step, I will now take my radical and I cut it up right there. I will split this a little bit into 2 pieces, into the cubic root out of 8y cubed times the cubic root out of 4x squared. And this first part right here, the cubic root out of 8 cubed, that will be just, well, the cubic root out of 8 is 2, and the cubic root out of y cubed is just y, times the cubic root out of 4x squared. So there is still, let me clean this up here a little bit, there is still a little bit radical left, but it is less than what we had to begin with. From now on, we are ignoring even and odd radicals, and we just always say that the nth root out of something raised to the n power will be just a. This is going to make things easier for us. And why can I do this? Because in the next example, we will always just say that I have not negative values inside my variables. Remember that we said that if n is even, then the nth root out of a to the n, strictly speaking, is the absolute value of a. This would just make our problems look more complicated. It would not be very interesting for the difficulty level. So we are just going to say, let's forget about that. And we are not considering negative values. So what I will do in this case down here, the 200x squared y, take the square root out of this. I will do now the same thing as I did a moment ago. I will attempt to split this into 2 factors, one being perfect, a perfect square in this case, and the second factor, if there is some, that will be then just the rest. So I look first at the numbers. The number 200, the coefficient. 200 is the same thing as 100 times 2. Now I start looking at my variables. And for my variables, I really just start looking at the exponents, and I wonder if the exponents in this case are divisible by 2. Why 2? Because this is the square root. So x to the second, 2 is divisible by 2, is a perfect square. And y to the first, 1 is not divisible by 2, so it comes to the part of the rest. Now what I'm allowed to do, I can now split this right here into two radicals into the square root of, let me rewrite this right here, this is 10x squared times the square root of 2y. And this first radical, the perfect one, is just going to open up. This is just going to be 10x, but I still have a little bit radical left. This is the square root of 2y. And you see, we used to say this 10x would have to be the absolute value of 10x, but we can forget about the absolute values from now on for the rest of this chapter. Let's do two more examples before we go and add an additional step in our simplifications. So we are supposed to simplify these two radicals. The first thing that I'm going to look at is the index of the radical. This is the square root. That means there is theoretically a 2 up there. That means now I will look at all of my exponents. I'm trying to grab just the exponents right there. And I will just look at whether or not these exponents are divisible by 2. If they are, then I'm great, then I'm perfect. But if they are not, then I just split this into two pieces so that it will be divisible by 2. Let me give you a quick example here that illustrates what we are talking about. If I would have the square roots of x to the 8th. Now 8 is divisible by 2. Why is this interesting? Because we have learned in the last section that I could rewrite this with a rational exponent. This is the same thing, x raised to the 8 over 2. And now 8 is divisible by 2. And this is why this is so nice, because at that moment it will be just x to the 4th. If I have something that is not divisible by 2, like x to the 9th, well, then what I will have to do is this. 9 is not, I could rewrite this x raised to the 9 over 2, but 9 is not divisible by 2. So I have a little bit of a problem. But what I can do is I can break this into two factors, x to the 8th times x to the 1st. And now I could break this into x to the 8th times the square roots of x. And I would end up with x raised to the 4th times the square roots of x. So all of these are the same things. This is the way that we want to rewrite this. All right, now we are ready to do this. So what I will do right here, I will split this into two factors. X raised to the 8th. There is still one x left because I have 9 exponents. Y raised to the 10th. There is still one y left because I had 11 exponents. Well, 11 to the 11th power, let's say it correct. Z to the 2nd. There is still a z to the 1st. Now I'm going to split this up into two pieces. And I will have the square root out of x to the 8th times y to the 10th times z squared multiplied by the square root of xyz. And the first one, all of these exponents now in my first radical are divisible by 2. So I get x to the 4th times y to the 5th times z. But a little bit of square root is left. The square root of xyz. All right, let's do the next one in the same way. Now I am looking at a 3, a cubic root. So instead of asking myself whether the exponent is divisible by 2, I'm asking if the exponent is divisible by 3. Everything else is the exact same thing. All right. So I will try to break this into two factors. Let's see, the number 40. 40 is 4 times 10, but 4 is a square, not a cube, but it is also 8 times 5. Now x to the 10th, 10 is not divisible by 3, but 9 is, and I still have 1x left. Y to the 14th, 14 is not divisible by 3, but 12 is. And I still have y to the 2nd power left. Now I split it into two radicals, into the cubic root out of 8 x to the 9th times y to the 12th multiplied by the cubic root of 5xy squared. And the first root is going to dissolve. It's going to open up because it's a perfect cubic root. The cubic root out of 8 is 2. Out of x to the 9th is 9 divided by 3 is 3. And y to the 12th, one moment, we cannot almost see the 12 up there. There you go. 12 is also divisible by 3. This will be y to the 4th. But I still have a little radical left, the cubic root out of 5xy squared. It's kind of like making pancakes. This right here is the last pancake that either is going to turn into a super pancake when you make pancakes, or it's going to be a little teeny tiny one. All right, now last example. We are now first multiplying and then simplifying. So we will do everything that we have done before. If you know how to do this problem, then you're good to go. So the first thing, and I'm going to skip a few steps here now to not have to write down too much, because sometimes this is just going to make it more complicated than it really has to be. This is going to be the cubic root. I was multiplying these two. That means I can multiply the radicands. 9 times 6, let's see, that is 30, no, not 30. 9 times 6, that is 40, 60 is 52. X to the 4th times x to the 5th, that will be x to the 9th. And y to the 10th times y to the 1st, that will be y to the 11th. Z to the 5th times z to the 2nd, this is going to be z to the 7th. So I'm just adding the exponents. Now I'm going to look at my numbers. The number 52. Does 52 have a perfect cube in it? Yes, it does. This is 27 times 2. Is it? Yes, it is. Oh, 54. All right, this didn't work. 54 is what we have right here. 9 times 6 is, of course, 54. All right, use your calculator if you want to. X to the 9th has an exponent that is divisible by 3. Y to the 11. 11 is not divisible by 3, but y to the 9th. And that means I still have two exponents, two factors of y left. Z to the 7th, well, z to the 6th will be working, and I have one z left. Now I'm going to split this up right here into two radicals, and that means that the cubic root out of 27 x to the 9th, y to the 9th, y, z to the 6th is just going to be 3 x to the 3rd, y to the 3rd, z to the 2nd. Really quickly, how did we get this? The cubic root out of 27 is 3. 9 divided by 3 is 3. 9 divided by 3 is 3. And 6 divided by 3 is 2. And I still have a little cubic root left, 2y squared times z. Let me give you a quick list of numbers that will help you to remember for the numbers what kind of perfect cubes we have. 8, 27, 64, 125, those are perfect cubes. 8 is the same thing as 2 cubed. 27 is 3 cubed. 64 is 4 cubed. And 125 is 5 cubed. And that will be enough for us to know. These are factors that we are looking at for the coefficients, or these numbers.